remained online for the following hour. I'm going to talk about some basic concepts of GIS. Why do we need it? What it is? Very high-level overview of the data types and GIS analysis methodology as well. And following me, Dr. Hu will introduce more of resources supporting COVID-19 research with GIS. So why do we do GIS? I think probably most of you understand that we are in the midst of the fourth industrial revolution. There's a surging tide with what someone summarized as ABCD. A as artificial intelligence, B as big data, C as cloud computing, and D as digital disruption. And you probably find different versions of these mixed it with Internet of Things, robotics, and blockchain, and everything else. But one characteristic in this surging tide is that geolocation becomes ubiquitous. Place and time are embedded in the data, in the methodology, and the analytics, and in the visualization. So if you look at the Millennium Project that had published a white paper on the 15 global challenges in the 31st century, you look at the 15 challenges, just about every one of them involves a spatial component, right? Sustainable development, climate change, clean water, right? Food, health, of course, we're in the middle of a pandemic, right? Conflicts, organized crime, energy, right? You name it. All these has a spatial component. So understanding our world in the spatial way is the key to solve these problems. And we can do that because geospatial and temporal data are everywhere nowadays. Unlike in the past, you go out and do a survey, it's very costly, very time consuming. Right now, there's so many gadgets deployed in space, on the ground, in our hands. There's the GPS, there's the Earth surveillance satellite, taking imageries. We have smartphones, car phones, cities, you name it. All of these are capturing a lot of data, right? Measurements, all with a space and time, location and time embedded in the data. So how do we use that to solve our problems? In general, the process is that data is flowing in, right? They're streaming in unprecedented speed and volume. We need to process it and organize it, like what Dr. Bao had explained earlier, integrate them, have a standard, so that it becomes useful and usable. Therefore, turn data into information, right? And then you would need to analyze it, explore it, simulate it, many different ways to analyze this and turn the information into knowledge. With that, and with our vision, right? And we gain a better understanding of the world and kind of distill this process into human wisdom. So that is why we need GIS. So what is really GIS in that sense? You could see it as a smart interactive functional map that is dynamic, you can print. You could also see it as a set of tools and procedures and a unique language to perform tasks, which is the analytical core of it. You could then also see it as a well-managed, well-organized system of information, a database, a systematic data archive. So the data is at the bottom, analytics is in the core. and the map or whatever visualization is on the surface. These are the three levels or three facets of GIS. And when we talk about doing GIS, you need software. Okay? One of those dominating software in the GIS industry is GIS by the company called ESRI. Probably most of you are already familiar with it. ArcGIS is not actually one piece of software. It is an overall name of the Esri Geospatial Information Systems family of products. It provides a standard-based platform for data management, for spatial analysis, and for mapping and visualization. So all three tiers are covered. And most of the time, I think people are using a desktop component. And for those of us who are in this field for many years, we probably know ArcMap, which is part of the ArcGIS desktop component. And the new users are probably more familiar with the online platform called ArcGIS Online. And in the middle is the new generation desktop tool that bridges the traditional desktop analytical platform with the online platform. It's called ArcGIS Pro. So most of you probably are already familiar with it. And also there's the mobile, there's the server, there's the living atlas of the world, right? Many, many different components forming this ArcGIS family. And in the rest of this talk today, I'm going to use this software as an example to introduce a basic concept of GIS. Now, that's not the only GIS you can use. There are so many other commercial and non-commercial tools out there. I'm not going to read the whole list here, but you will have the list as your reference, and you can try out the different things. Some of them are free, some of them are open source, some others are proprietary. Okay, so how does GIS organize data? There are basically two types of data, raster and vector. For raster data, it's like a picture, right? Every pixel in that picture represents some properties on the ground. For vector data, you have point, line, polygon. And then you have the coordinates of these locations plus a description, what we call tabular attributes, describing that location. So these are different forms of GIS data that we usually use. When you use a raster data set to represent reality, a point is represented as one pixel. A line is represented as a string of pixels connected to each other, right? And a polygon is a patch of adjacent pixels sharing the same value. So that's a raster representation. So when you get to the vector representation, a point becomes a pair of XY coordinates, right? And a line is a lot of points connected to each other, right? And a polygon is when a line loops back and the end point becomes the beginning point, then it forms a polygon. So you can see that there are different ways to abstract ground truth, ground objects into these numerical digital forms. And you can also see that the same ground object could be represented differently. For example, a city, when you're zoomed way out, it is one point, one XY coordinate. But when you zoomed way in, a city is definitely a polygon, not a point anymore, right? Same as highways. When you zoomed out, it's a line. When you zoomed in, it's a bell-shaped polygon. So these are abstractions of the reality. And why do we study that so intensely? Because it has unique properties. It records the location, the description about that location, which we call attributes, and the spatial relationships among them, how things are connected, what is next to what are overlapping with what, right? The scale is important, the resolution of the data is important, and also when you're flattening out a surface of a sphere onto a two-dimensional coordinate system, you have to transpose the location by a projection, and that introduces distortion. And also recording locations on surface of the Earth, which is not a perfect ball, is challenging. So the surveyors are defining the datum that we can anchor our measurements on. All these are very unique properties in GIS data. Just talking about a projection quickly, here are the different ways that you could try to peel an orange, lay it on the ground flat and without wear and tear, and try to do that, right? What you can do is you can sacrifice some part of the Earth to preserve some properties for areas that you're most interested in. Allow distortion in other unimportant areas by preserving accuracy on most important areas based on your purpose of the study. So these are many different ways. There are hundreds or thousands of different projection systems to help you project the ground to a 2D Cartesian system based on different objectives. Now, quickly moving on to GIS analysis. If we organize the different analytical approaches into categories, the first big category is exploration. You just want to look at the data. And then second, you want to do manipulation to the data and generate new data, right? For the exploration piece, quantitative mapping is very fundamental. And then location-based query is another that you can do. For the manipulation, right, data analysis, overlay is very common. Overlay, proximity analysis, network analysis. For example, here, when you do habitat suitability analysis, most of the time you would involve some type of overlay, right? Different properties overlap to each other, forming new properties for that piece of land. Here, another example is a hurricane damage assessment. This involves proximity because you have a hurricane track, and then to both sides of the track, the wind speed gradually reduces, and you can buffer out and then overlay it on your ground structure to see which one would be the most under the strongest wind impact, most vulnerable or critical facility in danger, and so on. So that's proximity analysis. And then here is an example of a network analysis when you're trying to study the connectivity of the electricity grid, for example. And there are many other, like river network, right? Many different transportation. All those are network analysis. Here is a spatial statistics analysis when you have to study the optimization for business hotspot analysis. Where are your customers? Where are your competitors? And where are the most dense area? Where there are anomalies for problems. So these are the different ways to analyze spatial data in GIS. And next, I'm going to use very quickly some examples from Harvard's researchers that we've had our staff at the Center for Geographic Analysis at Harvard University had the privilege to help conduct the analysis in all these different applications. So the first one I mentioned about quantitative mapping, which is to use a classification scheme to categorize the properties of an attribute in the GIS. data layer, and then so that you can see the pattern more distinctly. And here is one example of a teaching system that we developed for Harvard Business School in studying the historical global trade dynamics in the past 100 years. This system uses quantitative mapping basically to allow the professor in a class to pick a commodity, for example, coffee in this case, and then here's a time bar you can scroll through, and then see the different countries involved in exporting coffee products over different years. And quantitative mapping gives the color shade to allow the countries to be differentiated based on the volume of coffee export at any given year. Right? We've seen that too in a lot of other applications, so it's easy to understand. Now, location-based queries may be a little trickier. It is to select spatial attributes, spatial features based on where they are and what's their relationship in location from the current set of your starting point. So you could have select things that's adjacent or overlapping or within a certain distance and so on. You can define many different relationships here. And here is one example. This is done for, I believe, a health policy research project where we all know that in the United States, health insurance policies in the Affordable Care Act marketplace varies from location to location. Some places have many options. There are more companies participating in the Affordable Care Program, and some other places, there are not so many. So if you enter a county, not even by county, some are part of the county, you can see that you can select by the location of those insurance companies offering service there to see how many choices people living in that particular location would have, right? So you select the health insurance services available for your home address, for example, and you can see that, lighter the color, fewer the choice. So some of these places have very few choices versus the other places have more, like Southern California or Texas would have more choices versus Montana and Louisiana have very few choices. So moving on to not just to explore data, but also manipulate data and generate new data layers. Overlay is the first one, and there are many different ways to overlay data layers. One example here is this is a training workshop that we offered a few years back for studying the socioeconomic impacts of fracking. Fracking, probably most of you are familiar with. This is the extraction of oil and gas from very deep rock geological structures. So overlay analysis was applied here to study the geological formation that holds these natural resources, the platforms, the wells already drilled on them. The red ones are gas and the black ones are oil wells. And then overlay on top, demographic data, transportation data, administrative units, and crime incidents, and so on, so that you can see the impact of these extraction was booming in a few years back, right? So these areas had shouldered, well, they gained tremendously in the economic sense. You know, employment rate was very low and so on. Service was up, but then they had to shoulder a lot of healthcare burdens, crime was increased, pollution, and so on. So an overlay analysis gave us a quick picture in how to face these challenges caused by this fracking economic activity. Now, next, move on to proximity analysis. We talked about buffer, and there are other distance calculation and other tools that you can do proximity analysis. And one example here is a training, again, a training project that we provided to actually high school students. This is to train them to use their GPS-enabled camera. Their phone could do that, enable their GPS, and then take their phone as a camera, and go out and photo the billboards advertising tobacco. So when the picture is taken, there's the location embedded in that picture, and they come back and make a map showing where the billboards are that companies are advertising tobaccos, and then buffer that out. Once you buffer it out, you know that schools, even having these billboards are very close to middle school, to high school. We exposed the vulnerability of these kids when they are surrounded by these advertisements for tobacco around their schools. So the students were learning a skill, and they're also learning to deal a problem that they face as students, as teenagers. Okay, network analysis is the next one. We use it oftentimes to trace connectivity, flow capacity along defined routes, and rate of flow, direction of flow, and so on. If you bring up, say, Google or any of the navigational maps, you're actually doing network analysis, and it may or may not know it, but that the underlying algorithm is part of network analysis. So here is one example that we used that to solve a problem. This is in Mexico City, when a hospital system, it's a company running multiple hospitals, they do cataract surgery, and they're looking for some new sites to place their hospitals that can provide that surgical procedure for people. But they want to find the site which is close to the diagnostic center. Therefore, patients, once they're diagnosed, can go conveniently to a hospital to have the surgery performed. But this type of closeness I highlighted here, right? How do you define closeness? You cannot do a straight line distance. What if it's a river in between, right? Close is not by straight line distance, but by connectivity through transportation routes. So you can do it. You can do your distance calculation by distance along passage, right? Driving distance, walking distance, or any other public transit distance. They are all defined differently. So the closeness is by travel time rather than by and a certain travel means, rather by straight line or even just basic distance along a route. So last is a statistical analysis, spatial statistics and geostatistics. these are very special analysis that takes space into consideration when it explores the data. Spatial statistics pretty much explores the data, and geostatistics predicts. Right? But so you explore such as the spatial distribution, like mean centers, directional trends. You use it to identify hotspots, cold spots, based on the value contrast between your focal point and the surrounding objects. You could also see a clustering or dispersion type of distribution pattern. You can interpolate values where you didn't take measurements. So all these are very space or location centric statistical algorithms. And here's one example, which is analyzing geo-tweets, right? We know tweets, and some of the tweets, when they were sent, the user had their device GPS turned on, so their tweets had a lat-long location marked on them. And we harvested all the tweets that has a lat-long location associated with it, and then fed it into our fast big data platform. So you can see that there are, hundreds of thousands of tweets for this one filter that we can filter by keywords, by location, by time, and then also by sentiment, meaning when people tweet about a certain thing, are they happy or are they not happy? What is the emotion? I apologize for the resolution of this image, but really what this means is negative attitude versus positive attitude towards the keyword mask. This is a recent study trying to gauge people's attitude towards the PPE, towards the protective measures. You can see that as time goes by, people are more and more agitated by masks. When they talk about masks, they're angry, they're anxious, they're worried. The positive, joking or happy comments about masks are much fewer than the positive ones. And the map here, the reason that I introduce it as a spatial statistics case is because these are kernel density maps, the heat maps, so that there are too many tweets to show one point at a time. Therefore, we aggregate that together, and the more intense you see, it's more tweets at that location. Okay, so that's a statistical measure aggregating spatial data. Now, last, I want to also mention a very comprehensive project, which is called the U.S. Cluster Mapping Project. This is a multi-year, high-profile project conducted by Dr. Michael Porter and his team in Harvard Business School, which studies the economic and industry relationships across the U.S. in multiple years. This one involved just about any and all different analytical approaches you could imagine. The cluster here is not just a spatial cluster, but also industrial cluster. So it studies the upstream versus downstream relationship of different industry sectors. For example, the steel industry is upstream than the automobile industry, and automobile production is upstream, and downstream is the car dealers and repair shops and so on, right? So you can see that there's the education sector, there's the entertainment sector, many different lines of industry that they cluster both in their business line, but also regionally. There are lots of regional centers. Those are the economic engines driving development in that area. So this, I would highly recommend that you check it out. You can see many good examples of both spatial, but also involving many other analytical methodologies in there. So with that, I'm going to hand this over. I'll stop sharing and let Dr. Hu introduce his part.
Andy, so you can see my screen now?
Yes.
Okay, great. Okay, next, I will talk about how to use the GIS resources to support COVID-19 research. So here is an example in the King County of Washington State. So this, you can see there are numbers here. These are the changes from different perspectives, including economics, social, and health. So from the economics perspective, the unemployment rate, the unemployment numbers, the housing assistance rate, and also is getting higher. However, the number of traffic is getting lower. From the social side, the food insecurity problems is getting higher, and domestic violence is getting higher. And for the health issues, especially for the medical aid, the application, the number is getting higher, and the health critical crisis line is getting higher as well. So you can see these are the differences before and during the pandemic. So what we can do to understand more about the pandemic? The data is always the most fundamental and important for the study. So we started to connect the COVID-19 datasets and data sources since January and found there were several limitations of the data sources. The first one is some data sources are fragmented information, and the second is some data sources are incomparable, the lack of standard to associate each other, and third one is the lack of spatial information. So they're not able to tell the spatial temporal patterns. And the last one is they just provide the temporal data collections. So what we want to do is to integrate the data from different data sources, and we also want to standardize and integrate the data and maps to make sure that all the data can be associated with each other, can link with each other. And finally, we want to provide permanent collections for the. So what data we have connected? So actually, this is a connected work by Harvard University and the China Data Institute, George Mason University, and Wuhan University, and so many other universities. So till now, we have connected over 100 data sources, and after we process, analyze, and integrate data sets, we have created over 70 data sets, including the confirmed cases, the healthcare workers data sets, and the global news data sets, some economics and human mobility data sets, and environment data sets, etc. And all these data sets are published on Harvard Dataverse or the GitHub. And so for some data private, we're only available to the cloud platform. And finally, we provide one data portal which can be used to access all the data sets. So this is procedures about how we can validate and sharing the data sets. And this is about how we connect all the data. We use the base map to associate each other to make sure that all the data can be associate each other, and we can can provide the spatial analysis based base map. And I mentioned, so all the data sets are shared on Harvard Dataverse. And the Harvard Dataverse is an online data repository for data sharing, preservation, citation, and exploration. What the most important part is it provides. The most important part is provides a permanent digital object identifier, which is also known as DOI number for each dataset. So, and the other important the resource is the spatial data lab. So as I said in the data sets are private, and so they are only available to be published on spatial data lab. So there are 4 important components in spatial data lab. One is data library, which can be used to share all the data sets among the users. The second is an analytical lab, which provides the tools, a variety of tools to analyze the data and can be and share the data, the tools and processing results. And the third one is collaboration lab. So all the data and tools, the procedures and the results can be shared among researchers on the lab. And finally, it is also a training center. It can be used to for educating and training. So these are the data sources that we have saved on the spatial data lab. And until now, as of August 11, so there are the global users from over 150 countries and regions have accessed our datasets and download access for over 250 times. And also over 100 researchers have applied to use our platform, SDL platform, for the COVID-19 research. And this research topics covers like health equality, economics, some public opinions, and also the virus spreading. So based on the data we have connected and also the other resources we have, we want to answer some mainly COVID-19 questions from the spatial temporal analysis perspective. And here is one example. The first one is how did the virus spread worldwide? So this is other screenshots of our animated map. It's a dynamic map created by us. So from the map, we can see that in January, China is the hotspot of COVID-19 pandemic. In March, the disease have transmitted to lots of countries. And in May, the US is the hotspot, the most cases. But when it comes to the end of July, not only US, United States, but also Brazil, Russia, and India has become the pandemic centers. And there's the second question is how the global policies involved and how the outbreak was controlled or not controlled. So these policies are quantified by stringency index estimated by Oxford University. This index covers more detailed indicators, including school closures, the working place closing, public event, stay-at-home requirements, economic response, and health response. So the Oxford University connect all these data, policy data across all over the world, and we create these spatial temporal maps to understand the policy stringency changes over time during the pandemic. So the darker of the color indicates higher value of stringency index. So you can see that, so before the March, China has the largest stringency values because China is the first pandemic center. And after April, so since the disease has transmitted to many countries, so these countries have published policies to slow down the COVID-19 pandemic and outbreak. And I want to mention there is the country of the United States. So you can see that United States after April, the color is getting darker, indicates the stringency index, the value is getting higher because of the outbreak in the US. However, after in July, the stringency index is getting lower because some states in the US has the active demand of open economics. So this with the reality that some states in July as the pandemic is getting worse. So next question is how are people movement changing in the United States? So we answer this question based on the geotech tweets. So when the geotech tweets to analyze the sentiment, to find the sentiment trends over time. So the geotech tweets can also be used to detect the more population movements. So if a user posts tweets in different cities in day 1 and day 2, so we'll create a link here. And finally, will becomes a network. You can see the population movement decline dramatically from in. Hi, could you mute yourself? Thanks. So you can see that the population movement declined dramatically from in March and April, and however it starts to decrease in May and June. You can see the curves here is going down first and then start to climb. So this movement change should reveal the impact of COVID-19 as well as the mitigation policies on people's travel. So this work is done, actually it was done on another collaborator, University of South Carolina. The next question is how our community activities change. So this is the data is from the Google Community Mobility Reports. So the Google Mobility Reports look inside, provide insights into changes in the movement trends over time in different countries, categories of places, such as the grocery stores and pharmacies, parks, transit stations, retails and recreations, workspace, and a residential area. So you can see the visit to the public places such as park and groceries decreased significantly as the outbreak of COVID-19 swept over across the world. And activities at home increased dramatically as the result of stay-at-home or work-from-home policies. As the situation turns better in some regions and countries, the visit to public places such as workplace, parks, have increased gradually since late May. So this is the last question about knowledge is about how human activities are impacted by the pandemic. So to answer this question, we use the lifetime light image. Lifetime light images is always considered to estimate human activities and also the. So there are two images here. So on the left is a lifetime image. So in December 2019. So and this image on the right is in February 2020 in Wuhan. So Wuhan is the city that first detected COVID-19. So you can see that compare these two images, you can find some regions are dimmer during lockdown in February compared to December 2019. And also there was another figures here. So in this figure, so different colors indicate different kind of categories. So the blue colors indicates the residential area, and the yellow color indicates the traffic area, and the gray color indicates the commercial centers. So based on the charts, you can see that there are significant more pixels in the residential categories, but more pixels in the commercial centers compared to the values in December 2019. Based on the studies, we can see that based on the GIS methods, we can efficiently to find the spatial temporal patterns of COVID-19 impact on and also environment. So next is, I think, Wendy.
Let me switch back the screen share.
Okay.
Okay. Thank you, Dr. Hu. So let me quickly wrap up. I know time is about up. Just a quick summary that the value of GIS, you can see from the examples that it provides a framework for us to organize our knowledge, right, geographically. And it reviews patterns and relationships and processes so that we can understand better our world. It also helps us conceptualize, represent, and communicate ideas, whether it's about the past, the present, or the future, right? The learning GIS really is a lifelong journey. It's not something that you could just, pick it up and be set with your life, right? So here, just for this one software called GIS Pro, yes, this the center circle that I showed earlier. The functionality of it, over here, I just opened up the toolbox, right? There are that many tools, and I happen to just open the first one, and you can see how many just in the first one and the first subset, right? So if you go to the next one, the analysis tools, it's too long. Look at the bar. It's too long that we can't even see how many more are in there. So software are very powerful, but you can't just blindly hit the hammer and hope that it will tell you what you want to get. You really need to understand what's behind the scene, how the developers have put the tools together, and what did it do for on your data, so that your conclusions really make sense. So, and besides, that was just the core of our GIS Pro's toolbox. And it has many different modules, called extensions also, that gives you even more double, triple, quadruple tools that you could use. So it's really not something you can take on so lightly, but it's very, very powerful that you can do a lot of things with it. Today is not the time to go over the details, but I want to share some links with you. So those of you who want to learn more, to start from the tutorials and self-learning videos from these websites. And we want to, for wrapping up, we want to thank all our collaborators, of course. I think many of these you can see are also collaborating with Dr. Bao's China Data Institute, and then even more are with our team and the analytical side of it too. And I also want to mention that we receive NSF grants in supporting part of this work. So thank you very much. I'll stop sharing and address questions if there's any.